Hi all, I'm going to talk about how to do the programming for dummy coding. Here is our dummy coding equation. Y hat equals an intercept, a constant, plus a weight that is multiplied by one of the dummy codes, plus another weight times another dummy code. This is for a one variable with three levels. So the variable is conditioned. The three levels are high dose, low dose, and placebo control. If I have three categories, three groups, I need a set of two dummy codes to represent those. 100100 is my standard dummy code. When I plug those in, I am going to be able to reproduce the means of the three groups. The 10 gets plugged in so that B0 plus B1 gives me the mean of the high dose. The 01 gets plugged in so that the B0 plus the B2 gives me the mean of the low dose. And the 00 gets plugged in, so just the B0 is the mean of the placebo control. Hence, whenever I look at this equation and see values, I know that the B0 is already giving me the mean of the control group. The B1 is telling me the difference between that reference point and the mean of the first group that I've designated, D1, and the second one is giving me the difference between the reference point of B0 and the mean for the low dose group. So that's our review. This becomes more useful once we start talking about the ANCOVA design, where we actually put in a predictor such as X, and then we have a set of dummy codes. And all of this is leading up to where it becomes extremely useful, and that is when we get interaction effects, because that is what the general linear model, as you approach it from an ANOVA standpoint, is not good at dissecting and putting all the pieces together. So all this is learning to get up to that point, basically. Okay, so how do we do the computer programming part? So I have my data set over here. I want to go ahead and take out these codes. And SPSS is really straightforward in terms of its statements. There's basically two types of statements. One is a compute statement, such as compute high dose equals 0. And I'm going to say execute. And I'm going to go over here, run that, and you notice that what it did was it stuck in a new variable called high dose, and it made the values all equal to 0. So that's the simplest type of statement. It gets useful as well for when you need to, center a variable, which we'll come back to. The other basic type of statement in SPSS that's really, really easy to use is an if statement. And here I have examples of the if statement, and here I'm basically taking if drug condition equals 1 or drug condition equals 2, then high dose is equal to 0. If I made all of the variables of all of high dose equal to 0 to start off with, I don't even need that. And I could just jump down here to execute. And then if drug dose is equal to 3, oh, sorry. I named this differently, so I do need that. Let me get rid of those two. So when I run this, it It has run, but it's not showing me what's going on here. It won't do that until it reaches an executable statement. An executable statement could be correlations, regressions, one way. Those are all what are referred to as executable statement. That is a starter routine. If I want my values to show up, I can just say execute what I've already run, which is the reason why I tend to write execute after my statements. Execute. And now it has executed these two statements. It's put in zeros for drug condition 2, drug condition 1, and it's put in ones for drug condition 3. And then we can go ahead and do this for low dose. We're going to want the ones and the threes to be 0. So if drug condition equals 1 or drug condition equals 3, so you use and or ors are possible within the if statement to designate exactly what you want. And then say, and if drug condition equals 2, low dose equals 1. So I like to, specify what my 0 values are, then give the other values equal to 1, and then run that, and there I have it. I'll show you another way of doing that. If I take out my low dose and then write compute low dose equals 0, what it did was it made all of the values equal to 0 first. Let me show you that again. Execute. I'm just going to run this first part. So it makes all the values low dose equal to 0. Which is a faster statement to write than if drug condition equals 1 or drug condition equals 3. And then says if drug dose is equal to 2, then change that to equal 1. So now when I run this statement after the first one, it redefines the values for condition equals 2 to 1 from the zeros. Of course, the important thing about running those statements that way is the order of the statements, right? Because the way that I had it constructed first, it doesn't matter which order you run it in, but if now I go ahead and say this and put in if drug condition equals 2 and then compute low dose equals 0, well, it ends up with low dose equals 0 as the last command that it followed, so it made it all 0. So back to the clean and simple. This specifies exactly what I want to happen for each condition. Run that, and there I have my set of dummy codes. Okay. Once I have my set of dummy codes, how do I run this equation? I'm just going to go to Analyze, Regression, Linear, and let me reset. I'm looking at bad behaviors as a function of high dose and low dose. I'm just going to go ahead and put those in together. And here's what I get out. I'm accounting for 67% of the variance, and it's significant with an F of 12.206 with 2 and 12 degrees of freedom. This shows up the same way in my ANOVA table, since this one step is consistent with the whole model. And then here's my B weights at the bottom. Again, the constant is the mean for my control group. So that's the placebo control. The high dose gives me a minus 5.64. So that's referencing the difference between that and the placebo control. So it's 5.6 less bad behaviors than in the placebo control. So you take the 8.4 minus the 5.6, and you're going to get around 2.8, I think, something like in that neighborhood. And that's going to be the mean for your high dose group. And then 8.4 minus 3.2 is going to give you the mean for the low dose group. So this tells you directly that the high dose gives you significantly less bad behaviors than the placebo control. And the low dose does as well, although obviously the effect is not as strong for the low dose, kind of consistent with what we might imagine. You notice that the zero order correlation for the low dose is non-significant, but it's really not interpretable because the high dose and low dose are correlated with one another, as we've talked about. So if I put in bad behavior, high dose and low dose, I see that high dose and low dose share a correlation of minus 0.5. And hence that set of dummy codes is not consistent with what happens once you control for high dose. What happens with low dose is not consistent with what happens once you control for high dose. When you have a non-orthogonal set of codes, as in dummy coding or effect coding, you have to look at those codes as a set. And that preserves your ability to use a ANOVA type language. Let's go ahead and run an analysis of covariance. Typical analysis of covariance model would be to take age, put in on the first step, then hit next, put in high dose and low dose on the second step, make sure that we click our R-squared change, hit continue, hit OK, and now we see that age does significantly predict the number of behaviors. That direction of that result down here you can see is positive. The older the children are, the more bad behaviors they're exhibiting. But we still have a highly significant effect, even controlling for age, for drug condition. And that's the way to say it. We have two variables, low dose and high dose, but together they represent all three levels of our variable drug condition. Because when they're zeroed out, they still represent the placebo control as well. You have to keep that in mind. So all three levels are represented in the variable drug condition. And the fact that I've entered them as a set allows me to use a ANOVA style language of saying that drug condition with all three levels shows significant differences. And then when I look down, and I would report that with a delta F or F change of 8.606 with 2 and 11 degrees of freedom. When I get down over here, I find that my age variable is no longer significant, but it's okay. If I wanted to control for it, I wanted to control for it. And so my high dose still shows a significant decrease. My low dose still shows a significant decrease. The 4.822 here represents the average number of bad behaviors of the children. And it was previously 8, But this is for children who have ages of 0, because the constant always represents what happens when all of the variables in the model equals 0. So going back over to this equation here, which is the way that I like to specify the ANCOVA model, the y-intercept, the constant B0, always comes out as the value when x is equal to 0, when d1 is equal to 0, when d2 is equal to 0. I've put in brackets here the dummy code, so to represent they're being entered in as a set. So I entered in x1 first, and then for a second set, the set of dummy codes. But the intercept, the constant, is when x is 0, d1 is 0, d2 is 0. Now, x being 0 means nothing here, right? It's weird because there's no kids in the sample that have ages of 0. So if I want to make this more interpretable, I can do that by basically centering my data. How do I center my data? So let's do that. First, I need to know what the mean of the ages is. So I'm just going to go and run a quick descriptives. Descriptives age equals, and it turns out that the mean is 8.33. 8.33 with a simple descriptive statement. So knowing that, I write compute centered age, just make up a new variable, equals age minus 8.33, and then close it off with a period. And then I'm going to write execute. And there's my centered age variable. And now I'm going to run a regression where I go back to my first step and put in centered age. Everything comes out exactly the same as when I had in age. It makes no difference in terms of the inferences I'm making. Everything is significant, exactly the same. The standardized coefficients are exactly the same. Even these coefficients here are exactly the same. The only thing that's changed is the constant, but the constant now represents something more interpretable. It means that on average for these data, the kids in the placebo control who were zeroed out have a average number of bad behaviors of 8.062. Okay, let's move ahead and talk about effects coding. So here's our effects coding system. And here I have used a trick for being able to not specify everything with if statements. I basically started off by saying, okay, let's compute a variable called high dose underscore E for effects coding, and let's make that equal to the ones and zeros that I have for my previous high dose variable, and over here for the low dose variable, make those equal. So if I just go ahead and execute those to start off with, you'll notice that what it does is throws in the two new variables, but they're constructed exactly the same way as my dummy coded variables. And now I'm going to go ahead and say execute, and where drug condition is equal to 1, simply change those to negative ones. And there, it did that, change those to negative ones. And that's consistent with what we've talked about previously in class. Here's our effects coding system. High dose, 1, 0, low dose, 0, 1s, and placebo controls, -1, -1. And I've represented that here, changing out the names of the codes to E's for effects codings, and over here for my ANCOVA model, basically putting in the effects codes as a set. And if I want to run this in terms of the centered X, I might go ahead and note that as a centered X is the way that I like to notate it, as for my equation for the ANCOVA model. So let's go ahead and run the regression. Here I have it actually spelled out in syntax. So I'll just run it from here. And go to my output. And it's showing that the grand mean of the bad behaviors is 5.467, and then the difference for the low dose from the grand mean, the difference from the high dose from the grand mean. Remember that these values here are with reference to the constant. Whatever kind of coding scheme you've used is with reference to the constant when it is a dummy code, a contrast code, or to say a dummy code or effects code. It's with reference to the constant. It's not that case with a contrast code, sorry. And for the ANCOVA model, you'll notice that the way that I specified that here in syntax is to enter age first, enter then in the low dose and the high dose. So I'm going to go ahead and run that as my ANCOVA model. And we see our constant is now 2.226. I didn't run the centered. So I'm just going to go back and rerun that real quick. Go over here, back to linear regression. And there I do have centered age. We've got those put in the effects codes and run that. And now my constant is back at 5.465, showing the effect of centered age, which is non-significant, but there is a slight increase. And then my low dose is a little bit below that, and non-significantly below the grand mean, and high dose is significantly below the grand mean. Again, our model summary is telling us exactly the same thing as the dummy codes. And it should, because it's basically just saying when I add in ANOVA language, drug condition or treatment condition, which represents all three levels, high dose, low dose, and control. So I get the same thing, controlling for age. My last model that I'm going to run is a contrast code. Um, and let's take a look at how we're doing that. Let me go over here to Word. Here's my contrast coding scheme. I'm going to designate the codes as test, and I'm going to call them test 1 and test 2. Test 1, I'm going to test high dose against low dose and placebo control. Actually, I don't want to do that. I want to test one against both treatments against placebo control. And then I'm going to zero out placebo control and test high dose versus low dose. There we go. So those are going to be my two tests that I do. I believe it's set up correctly in my syntax. And here's my designation for that test, putting in brackets the dummy codes to represent the fact that when I actually do the regression, I'm going to enter those as a set so that I can refer to them in ANOVA language and talk about whether or not the difference between all three of these levels of the one condition, the one variable, whether or not there are significant differences therein. The codes then tell me the nature of specific differences that I have coded for, whether that be dummy coding, effects coding, or contrast coding. Yeah, so placebo control is number 1, so that's a 2, then -1 for the others, and then zero out treatment control and look for a difference between the other two. Let's go ahead and see that when I enter it. And if I'm going to see it right, if I just basically go like that, it doesn't show up until I actually run a execute statement, or it'll show up when I run an executable statement such as regression. So I'll just go ahead and run that regression. You'll notice that they show up now. And let's find the output. And here's my output. And here's my basic ANOVA with 2 and 12 degrees of freedom. I have the same result. And then this is showing me that contrast, so these are not in reference to these. These are unique tests now, since they're not correlated. So this is showing me that I have a significant difference between high dose and low dose combined versus placebo control. So the drug treatments work. This is showing me that I have a marginal effect for high dose versus low dose. And finally, if I want to run that as a an ANCOVA model, I'm going to put in bad behaviors for my DV. I'm going to put in, let's go with centered age in block 1, and then test 2, test 3 in block 2. We have enter for each of the blocks. We can get our R-squared change. And again, we see exactly the same results as what we've seen before. So there's nothing unique in our different coding schemes about the overall model change. But our coefficients down here now do tell us that there is a significant effect for the two treatments. It's showing that once you control for age, it's not marginal now, it's non-significant. No difference between high dose and low dose. We have very little power here though. So with very few participants. So that's that. That's how we do the coding schemes in on the computer. Hope this helps, and we'll see you for the next one.